Now the concept is about magnet. So we know magnet, it is having a power of attracting pieces of iron, right? So which can attract irons or some objects is called as magnet, which is, for example, if I am taking the shape of this, so naturally magnets are comparatively weak, so because of their rugged and clumsiness, these are called as natural magnets. And there are commercial magnets also. So natural magnets, they are rugged and clumsy. Coming to the commercial magnets, they are made artificially from iron and steel. Okay, so in this again, what is artificial means? So artificial magnets can be made either by rubbing a piece of iron or steel with the lodestone. So when you rub a piece of iron or steel with this lodestone, or by passing heavy direct current through a coil, when you are passing a heavy current through any coil also, heavy currents through coil over a piece of iron. So over a piece of iron, if you are passing heavy current carrying coil, so this will also form an artificial magnet. So for example, artificial magnets, we can consider the voltmeters and meters which we are designing. Okay, so magnets are classified as permanent and temporary. So permanent, it depends on the ability. Okay, here magnets which we are according to this unmagnetized piece of iron, which it is not magnetized, we need to magnetize an iron. If it is an unmagnetized piece of iron or any other magnetic material, the molecules are not arranged in this for an unmagnetized iron. But when a piece of iron is magnetized, if it is magnetized, then various molecules will be forced into more definite alignment, so that they will align together to attract or repel or whatever it is. Okay, so and their north poles and south poles, or south poles and north poles, they will try to attract. When all the molecules of the iron piece are arranged in such a way that all the north poles point in one direction, right, and all the south poles are in the opposite direction, then obviously the iron piece is known as magnetized, or of course we also call it as saturated. Okay, so after a magnetizing force, means we are applying some force, is removed from the piece of iron or the steel, because we are magnetizing by applying currents or something onto the iron steel, by rubbing it with a lodestone or something, whatever it is, we are trying to make an artificial magnet. So in that case, when you remove this force from the piece of the hardened steel or the iron, the molecules retain their positions indefinitely, because when the magnetic material is heated, its molecules vibrate more violently. Consequently, with the increase in temperature, what will happen? Individual molecular magnets get out of the alignment. First they are aligned because of the input you give, and they were coming back to their original position when the input was removed from them, right? So within the increase of the temperature or decrease of the temperature, they will first align and they get back to their original position, like that. So the magnetic strength of the magnetized bar is always reduced because of this alignment or non-alignment. So it is possible to partially or even completely destroy the magnetic properties of the material by heating the magnet. So at temperatures higher than a critical value called the Curie point, we call it as Curie point, where there is a particular value. If you are going beyond that value, obviously the temperature is high, so the ferromagnetic materials lose their magnetic properties also, so they can't behave like a magnet. So whatever the piece, whatever the material you are choosing to magnetize, you should be checking its temperature critical value, so that you are not going beyond the values. So like that, the magnetic materials are of types. So we are having paramagnetic materials. So these materials are not strongly attracted by a magnet, such as aluminium, uh, tin, then platinum, magnesium, all are known as paramagnetic materials. These are slightly magnetized when placed in a strong magnetic field. Okay. Then coming to the diamagnetic materials. So coming to this diamagnetic materials, these materials which are repelled by a magnet is such as zinc, mercury, lead, sulfur, copper, silver, wood, etc. Whatever it is, those will come under diamagnetic materials. Permanent magnetic dipoles are absent in them. There is no permanent magnetic dipole. And coming to the ferromagnetic. So these materials which are strongly attracted by a magnet such as iron, steel, nickel, like that. So there are many things which can be attracted by magnet. So in our engineering, like in our electrical engineering, the materials are classified as ferro and non-ferro. So usually in electrical we consider ferro or non-ferro. Okay, so the non-ferromagnetic materials have relative permeability due to for the non-ferro, the relative permeability is closely equal to unity, and ferromagnetic materials have relative permeability many times greater than unity. That is the difference between ferro and non-ferro. So the paramagnetic and diamagnetic materials falls in non-ferromagnetic materials, because these two will come under non-ferro, and the one we use is mostly the ferro. Okay, so in ferromagnetic materials again we are having soft ferromagnetic materials and hard ferromagnetic materials. Soft ferromagnetic materials which are having extremely small hysteresis, and hard ferromagnetics are having a low permeability and very high force. So these are the types of soft and hard ferromagnetics we have. And coming to the magnetic field. So what do you mean by the magnetic field? So here we are talking about a magnet, right? So magnet means which is having two poles which can attract some materials. So when we are talking about that, we are obviously going to talk about the field around it, because as it is having some capability, some kind of force to attract or to repel. So if suppose this is the magnet, the field around it means, for example, this is the center of the magnet. If I take the center of the magnet like this, so then obviously what happens is, from here, so here to here, so as I go far away from the center line, the magnetic field strength will reduce. So for this magnet, the green place is called as magnetic field. So the space around the poles of the magnet is called as magnetic field. And these lines which whatever I showed, they are called as magnetic lines of force, because how they are attracting. N is directing that way, S is directing this way, north pole is directing that way, south pole is directing this way. So that way they will attract. So attraction will reduce, north south only. This small dot also will have north and south. Then what is magnetic force? The magnetic force, it is nothing but the force exerted on one magnet by another one. Means when you are keeping a magnet here and then another magnet here, here this is north south, this is south north. So south should attract north, north should attract south. So this force one on the other, either attraction, or sometimes if you are keeping north south and north south, they will repel. So either attraction or the repulsion is called as magnetic force. Because of the force only, either they might attract or they repel. So these things are explained by using Coulomb's law. So here we are considering Coulomb's law. So the Coulomb's law is saying that according to Coulomb's law, they have two laws. The first law says it can attract, the poles can attract or the poles can repel. Okay, so that is the first what we say, that is the first law. Okay, the first law decided the poles can attract and repel. Second law, after considering that, the second law was talking about, according to Coulomb's like second law, the force between two magnetic poles is directly proportional, like how in electricity we were talking, force is nothing but it is directly proportional to the charges. If there are two charges, we wrote like this, right? Q1 Q2 by d square. So finally we said F is equals to K Q1 Q2 by d square, where K is Q1 Q2 by 4 pi epsilon naught epsilon r d square. Epsilon naught is equals to 8.854 into 10 power minus 12. Epsilon r, if it is given, they will give the value. If not, it can be considered as unity, right? So this is the force we were talking in electricity about the charges. Okay, now here in magnetism, the same force is nothing but the force is directly proportional to the poles, north pole and south pole. How many north poles, how many south poles? So here we are talking about dipole, so it is talking about the pole strength. So we have two poles, right? So those two poles with their distance, the distance between the pole, the distance between the pole means it is talking about the size of the magnet. If it is a small magnet, distance between n and s is small. If it is a big magnet, the distance will be large, right? So like that it is talking. So to remove that proportionality constant, we are using K, m1 m2 by d square. What is K? m1 m2 by 4 pi mu naught mu r d square. Okay, so here these are called as permittivities. Here these are called as permeability. So according to permeability, mu naught is 4 pi into 10 power minus 7 mu r. This is also talking about the equilibrium, and here it can be 1 if it is not given. If it is given, we will take the same value. So that is the force between charges, force between poles. So almost the same. So little difference in taking the values. Okay, so this is Coulomb's second law. So the force of attraction or repulsion between the poles of m1 and m2 Webers placed distance with a d meters apart in any medium is given by this formula. Okay, so here relative permeability is this, here permittivity is this. Okay, so for example, let me do a problem on this. So to do a problem on this, they were giving a question saying two magnetic poles. So they said we have two magnetic poles. So two magnetic poles of strength. So they said strength is 0.005 and 0.01 Webers. Okay, so magnetic poles. So obviously this can be m1, this can be m2, are placed at a distance of 5 centimeters. So d is 5 centimeters. It means we need to convert it into meters. So meters in air. So obviously mu r will be 1. Determine the force between them in nature. So what is the force? So according to the concept we learned in magnetism, what did we learn? F is equals to m1 m2 by 4 pi mu naught mu r d square. So what is m1? 0.005. What is m2? 0.01 divided by 4 pi. What is mu naught? Mu naught is again 4 pi. So two 4 pi's will be there in the equation. Don't get confused. So 4 pi into 10 power minus 7, because this 4 pi into 10 power minus 7 is mu naught. This 4 pi is belonging to force. There are two 4 pi's. Okay, so then distance is given as 0.05 but d square, so it is 0.05 whole square. So if you calculate, you should get 1.266. Okay, that will be your answer. So since the poles are of same nature, because they said find the force between them with its nature, so it means they are in the same nature. So the force experienced will be repulsion only, because both are of same nature. Same nature means either it might be south or it might be north. So it means they are repelling. How much force is there between them to repel? It is 1.266 newtons. Okay, so that is the problem. So let's try to do another problem. The question is saying two magnetic poles, each of pole strength 10 milliwebers. So each of means m1 m2 both are of same. So as milli is given, we can say it as 10 into 10 power minus 3. So this is also 10 into 10 power minus 3. Okay, so okay, so two magnetic poles each of 10 milliwebers experiencing a force of 2530 newtons. So force is given when placed in air. In air means mu r is 1. See here I didn't write a mu r because it's 1. I think it's better I write, okay, mu r is 1. Okay, yes, so here mu r, then mu r is in air. So determine the distance between them. So they are questioning about that distance. So when they are questioning about the distance, first we should talk about the formula. F is equals to m1 m2 by 4 pi into 4 pi into 10 power minus 7, which is mu naught, into mu r is 1, in multiply d square. So d square I am sending it this way, f I am bringing down. So denominator went to numerator, numerator came to denominator. So m1 m2 by 4 pi multiply 10 power minus 2 multiply force. What is force? 2530. So what is m1 m2? 10 into 10 power minus 3 multiply 10 multiply 10 power minus 3, that is m1 and m2, divided by 4 pi multiply 10 power minus 2 multiply 2530. So find this answer. You will get an answer. Make it as a square root of, because it is d square, so d should be square root of. So you should get 0.05 meters. Okay, so that should be your answer. So formula is questioning about distance, but we have is about f. So we moved d to the left and f to the right. So as it is in numerator came to denominator, as it is in denominator it went into numerator. So finally we got distance as 0.05. So that is how we are talking. Okay, so our next concept is about lines in the magnetic field. So for example, when there is a magnet like this with the north pole and a south pole, so I am talking about the attraction of the poles. So this way and this way. So as we go far, the field strength reduces. So this is how a magnetic lines will be there in a magnet. So those lines are called as magnetic field lines. Okay, so when there is a line, so the magnetic lines of force is defined as the curve along with a unit n pole. It means an unit n pole would move if free to do so when placed in a magnetic field. So whenever it is giving a force, and here it will be like pulling off. Okay, when you come near, means when you, for example, I am taking another magnet. So this is my magnet. So this magnet is going until here. This magnet, for example, this is a magnet. This magnet will also have some magnetic field. Okay, for example, this magnetic field is here. Let's think the magnetic field is like this. So there is a gap between the magnetic fields, they won't attract. So it went further close. Then magnetic field is like this. Then what happens? This magnetic field are either attracted or repelled on the way of the direction. So now slowly the force has started. Now when you're going closer further, the force will increase. So it will attract faster. That's why the magnets, when they are far, it's okay. But when they are coming near, it will be very attractive to attract very fast, or very fast to repel even. So north and south pole, when you are bringing together, even a person is in between those two, if the size is too much, and if a big person is in between them also, they will crush the person also. That much attractive force will be there between them. So depending upon the size, the strength increases. So these magnetic lines are having some properties, like each line, you can see I just drawn few lines, but every line, each line of the magnetic flux forms a closed loop, like how I showed in the dotted line. This means that a line of flux emerges from any point at end of the magnet, passing through the surrounding space back to the south pole, from north to south. So they are passing by. So there is an loop here. So the line of the magnetic flux never intersect. So the line of the magnetic flux tend to contract lengthwise. So depending on the lengthwise and sideways also. So lines of force from the terminate on a surface normally. So what do you mean by lines of induction? So the lines of the magnetic flux traveling from north to south extremely and continue to travel throughout the magnet, so that they can act fast, and finally they reach the north pole, again forming closed curves. So the portion of the curves within the magnetic material called as lines of induction. What do you mean by magnetic flux? So magnetic flux is nothing but the total number of lines of force comprising with the field. How many lines are there? It shows how much strength it has. If the lines are less, means the strength is less. If the lines are more, strength is more, means magnetic flux is more. Okay. So what do you mean by magnetic flux density? So the magnetic flux density is defined as the magnetic flux passing per unit area. Means depending upon the size of the magnet. If magnet is small, its flux will be less, density will be less. Now this is the magnet. Now this is the big magnet. Obviously its density increases because the size has increased, because we are having more magnetic lines. So it is represented by letter B, which is called as magnetic flux density. So this is magnetic flux and this is magnetic flux density. So these are the symbols. So here we can say magnetic flux density is nothing but magnetic flux with its area, because depending upon the area only, quantity of the magnetic flux will be there, means magnetic flux. That magnetic flux with the area defines how much density we have. Okay, density means total amount of, on and total is nothing but the flux and the area of the magnet. So what is the relation between this magnetic field strength and magnetic flux density? So the magnetic field strength, the magnetic field strength, okay, and magnetic flux density. So the field strength, we are saying it as H, magnetic flux density, we are saying it as B. The magnetic field strength means there is the strength of the magnet. Density means because of the strength, how much flux has been induced and what is the density of it. So both are different, and what is the relation between them? This is what we are talking about. So at any point in the magnetic field here, the field strength is the force that maintains the magnetic flux. As the area reduces, flux reduces. As the area increases, flux increases. As the area increases, flux increases, flux density also increases, right? So thus the magnetic flux density can be assumed to be proportional to the field. Okay, so that's why we can say that the flux density is proportional to the magnetic field strength. To remove that proportionality, we are using mu. Mu means it is the magnetic space constant. Okay, so here we are talking about magnetic susceptibility also. What do you mean by magnetic susceptibility? It is nothing but the magnetization of the material which is proportional to the applied field and the proportionality constant. Okay. In other words, we can say that magnetic susceptibility is defined as the ratio of magnetization to magnetic force. Okay. So we can say susceptibility is equals to m by h, or we can even say m is equals to susceptibility into h, or we can even say h is equals to m by susceptibility. Depending upon your requirement, we can choose whatever we have. So far, what are the parameters we were talking about? We were talking about magnetic flux density. We are talking about magnetic field intensity. We were talking about magnetization, and at the same way we are talking about permeability. So what is the relation between them? We can easily say B is equals to mu naught into H plus M. Okay. So permeability is showing like this. Okay. So here B is equals to mu naught into H plus M. This is the relation between the magnetic field parameters. So these are called as parameters for magnetic field. Okay. So magnetic field parameters are magnetic flux density, magnetic field intensity, magnetization, permeability, and the relation between them is B is equals to mu naught into H plus M. Okay. So that is the relation. So let us do a problem on that. So for example, here the question is about find the magnitude of flux density. So they are asking us to find the magnitude of flux density in a material. So we need is B. Flux density means B, right? So this is the question. For what? First they are saying the magnetization is 2.8. So magnetization is 2.8 ampere per meter, and the magnetic susceptibility is 0.0025. So in the first point they gave these two values. They are asking us to find B. So what is the formula we are having? Here itself the formula is there. We know that B is equals to mu naught into H plus M. M, it is given mu naught, 4 pi into 10 power minus 7, we know that, but H we don't know. So to find H, we know the formula. H is equals to magnetization by susceptibility. So we know susceptibility, we know M. So we can substitute those two values and you can find the magnetic field intensity. So once you get the magnetic field intensity, you know all the things. So it's not a big job to find the magnetic field intensity. Sorry, magnetic flux density. Okay. So always you should remember the formulas, how to relate them according to the given question. So that is the main challenge. Okay. So then the second question. So the second question is talking about the information. The magnetic field intensity is given. So they give the magnetic field intensity as 1300 ampere per meter and the relative permeability. Okay. So the relative permeability is given as 1.006. So H is given as 300. Relative permeability is given as 1.006. So now they are asking us to find the flux density. So the flux density can also be written as mu naught mu r into H. Mu naught, you know, 4 pi into 10 power minus 7. Mu r, they already gave. H, they already gave. It's a direct substitution. So not a problem. Next, third point. In the third point, they were giving the number of magnetic dipoles per unit volume. So they gave dipoles, means how many poles are there in the system. So number of dipoles were given, means for example north pole and south pole both are called as dipoles. North and south as treated as single alignment. So like that there are 8.2 into 10 power 28 alignments. Okay. And they gave the dipole moment. So the dipole moment is also given as 3 into 10 power minus 30 ampere meter square. And they gave the magnetic susceptibility also. So the magnetic susceptibility is given as 2 into 10 power minus 4. So now the question is about B, magnetic flux density. But we know that magnetic flux density is equals to mu naught into H plus M. Mu naught we know, H we don't know. So I can say H is equals to M by susceptibility. Susceptibility I have, but I don't know M. Anyhow, I need M here also, I need M here also. So I want to find M. So according to M, I can say magnetization is nothing but number of dipoles into its dipole moment. So number of dipoles into dipole moment will give me M. M by susceptibility will give me H. H and M with mu naught will give me flux density. So you should know all these formulas. So write down the formulas, write down the relations. So the ones in the green are important to remember to solve these problems. So that is what we should remember. Okay. Yes. So now next. So next we are talking about magnetic field between two opposite poles. So for example, I am keeping a magnet like this, north pole, and I am keeping a south pole. It means of course north and south, south and north, that is how. Okay, I took a magnet. So now north is facing south. Okay, it means they can attract. So I am keeping a field with two opposite poles. Now the cross sectional area of the current carrying conductor is in a direction placed between the two magnets, so that this is the coil which I placed in the magnet. Now when I apply a current through the conductor by Fleming's right hand rule, so we can use Fleming's right hand rule. So by applying Fleming's right hand rule, the direction of the field current around the conductor, it comes like this. So this is going like this. Okay, it means it is this way, right? Then what is happening? North and south pole. North is attracting south, right? So this is going this way. Clear? So if the current carrying conductor is placed in the magnetic field, the resultant magnetic field will be similar, like this. Okay, so the lines of the force above the conductor are strengthened since they are in the same direction. Okay, these are strengthened as they are in the same direction. But the lines of the force between the conductor are weakened because the two fields between the conductor are opposite in direction, as this is north pole and this is the south pole, and hence they will destroy each other. So they will try to destroy each other. So the magnetic lines are like rubber bands, like how you stretch, they have the tendency to strengthen, and therefore a force is experienced on the conductor. Okay, if the direction of the current is reversed, this is the forward direction, but if it is reversed, so if it is reversed, then obviously hence it is observed that when a current carrying conductor is placed at right angle, the direction of the magnetic field, a mechanical force will be experienced on this. The direction of the force can be determined by applying Fleming's left hand rule also. After the direction will be experienced after a mechanical force is experienced. Okay, so when a mechanical force is experienced, the force experienced on this conductor is directly proportional to the flux density which is produced. So the force is directly proportional to the flux density, current flowing through the coil, and even the length of the conductor, because if the length of the conductor is big, current passage is more, so obviously flux will be more, flux density will be more. If the length is less, current will be less, flux density is less. So all these things can change the force as well. So I can say F is equals to BIL sin theta. Why am I bringing sin theta? Because in general, if the conductor lies at an angle theta with a magnetic field, then obviously it will create an angular notation. So that angular notation I am giving it as sin theta. So finally I can say the mechanical force experienced is F is equals to BIL sin theta. Okay. So let me do a problem on that. So here the question is given as length of the conductor is 2 meters, current is 40 amps, field strength is 1.5 Tesla, and they are asking us to find F, where the angle is a right angle. What do you mean by right angle? Right angle means this is right angle. It means angle is 90 degrees, means theta is 90 degrees. So this is the given question. So the given question is length is given, current is given, flux density is given, angle is given as right angle which is 90 degrees. So obviously I can say F is equals to BIL sin theta. BIL means B is 1.5, I is 40, L is 2 and sin theta is sin 90. So if you solve this you will get 120 newtons. So this is the force. Okay. So here this force is nothing but the force on the conductor when it is placed in between the magnets. And here there is another force which we are talking about. That force is just between the magnets. So the force F is equals to M1, M2. This is the force between two magnets. And this is the force between two magnets when they are placed with a centered coil. So both forces are different, but both belongs to magnet only. Clear? So that is magnetization. So magnetization about magnets, types of magnets, then force, and then another force. So this force is between two magnets with a coil. That force is just between two magnets. So magnetization, flux density, so susceptibility, all these parameters are coming. So this is about magnetization.